coming, everyone. Let's get started. Today we have Rajesh Jayaram, and he will be telling us about an FPRAS for counting path labelings. This is his best paper at POTS.
Thank you, Ainesh. Today I'm going to talk about an approximation algorithm for a certain class of structured path labelings, also known as the regular languages. This is sort of an overview of what the talk is going to consist of. So I'm going to spend almost the whole talk talking about a single result, which is going to be this one approximation algorithm. And so I'll begin with kind of introduction of the problem and sort of what's been done so far. And at the end, I'll have some open problems and actually some things to think about, hopefully. We'll begin with the introduction of the problem. So I'm going to start with the following fairly straightforward and simple problem. You may know the answer to this already, but I'm going to say it anyway because I think it'll give a sort of a good framework for how to think about the more general problem that I'll introduce in a minute. So I'm going to give you a graph G, a directed graph, and I'm just going to fix two vertices u and v in the graph, and then I'm going to give you some number n, and I'm just going to ask you to count the number of paths of length n from the vertex u to the vertex v. So I just want you to count paths. So for example, in this graph, I have two vertices u and v, and I could ask you to count the number of paths of length n equals 4 between u and v. And if that was the input, then the answer is easy to see. There's just three paths. There's one on top, and then there's another path down here, and then there's another path down here, all of length 4 between just two distinguished vertices. But what's the general algorithm? Well, of course, as you may know, this is sort of a common graph primitive that's used, counting paths. And the algorithm is just a straightforward dynamic programming algorithm. But the pictures in the overview is kind of useful, again, like I said, for the more general algorithm that I'm going to describe in this talk. So what's the algorithm? It's just a dynamic programming algorithm. Yeah, for every vertex in the graph and for every j less than n, I'm just going to store the number of paths of length j from the vertex u to the vertex x. And I'll call that njx. And if I want to compute njx, well, the number of paths of length j to the vertex x is just the sum of the number of paths of length j minus 1 to over all vertices y, such that there's an edge from y to x. So we can just,
Sorry to be pedantic, but a path can repeat a vertex?
Yes. It's just a sequence of edges. Important. So because all the vertices are different coming into the edge, we can just sum over all of them, and that will give us the right number of paths. And at the end, we just output the number of paths of length n going into our desired vertex v. And so this is a polynomial time algorithm that gives an exact solution for counting paths. Okay, so now I'm going to introduce the following slight augmentation of the problem. I'm just going to label the edges of the graph.
Well, it's not polynomial in n.
Oh, why not? So I'm going to compute each of these. Oh, so n is given to you. N is given to you in unary.
Thank you.
Okay. Yeah. This is okay. So yes, polynomial in n, not the representation of n. Okay. Good. So let me now introduce the following slight generalization. I'm going to assign all the edges a label. So this is just a function, and each edge I'm going to assign a label, some number 1 to k. And if I assign a labeling to each of my edges, then there's sort of a natural way to assign a labeling to a path. So if I have a path p, which consists of some sequence of edges, then the label of that path is just the sequence of labels of each of the edges. So label the first edge, label the second edge, and so on. And this is just an element in k to the n. Okay. So for example, if I just have this simple path of length 3 between these two vertices, this path has the label 0, 1, 0, because the first edge is label 0, the second edge is label 1, and the third edge is label 0. And by the way, for the rest of this talk, even though I defined it labelings into k here, we're going to just look at pictures that have labelings either 0 or 1, just for simplicity, because the problem is just as hard. Okay, so this is the example of what a label of a path is. And now I've actually defined everything I need to do to tell you what the problem that we're going to consider in this talk is. And the problem is as follows. I give you such a graph, and I give you u and v and an integer n. And the goal is to count the number of path labelings of length n from the vertex u to the vertex v. So I just want to count the size of this set, L of p, where p is a path from u to v of size n. And note this is different from counting paths because, as we'll see, two paths in the graph can have the same labeling. And we only want to count that labeling once. And so a very intimately related problem is the problem of sampling a path uniformly at random from this set. And we'll see why they're very closely related. And so these are the two problems that we're going to talk about in this talk. Okay. So, and for the rest of the talk, we're going to always fix these two vertices u and v. So u and v are always two fixed vertices in the fixed graph G, and they're always going to denote the start and end vertices of the paths we care about. And so I'm just going to drop the superscript here and write ln of G to denote the number of path labelings of length n from u to v. Okay, good. So here's an example of what makes this different from counting paths. Well, here's a graph where you have two paths of length 3 between the vertex u and the vertex v, but both of them have the same labeling. So I have the path 1 on the top, which has the label 0, 1, 0, and the path p2 at the bottom that has the same labeling 0, 1, 0. And so while we can count the number of paths here, and it's 2, there's only one labeling in this graph, and it's 0, 1, 0. So this is sort of the thing to keep in mind, which makes it different from counting paths. In fact, in general, we can have exponentially many paths in our graph that have the same labeling. And we don't want to overcount that labeling. So this is going to be the difficulty of the problem. Okay, good. So now I'm going to talk about where this problem comes up and why actually it's been a well-studied problem. And this is because it corresponds to a pretty fundamental problem, I think, in computer science, which is this problem in the setting of regular languages. So I can equivalently describe this problem in the following way. Given a regular language L, count the number of strings of length n in that regular language. So if you don't know what a regular language is, that's completely okay. If you do, well, essentially, you may recall that a regular language is just defined by the accepting strings of a finite automata A. A finite automata A is just a set of states, V. It's a set of labeled transitions, E, between those states. And then you just get a distinguished start and end state. So this is the same exact problem that we're looking at. It's just counting labeled paths in a graph between one fixed start state and one fixed end state. So it's the exact same problem.
Non-deterministic.
Yeah, we'll get to that. Yeah. I don't want to say anything about that just yet. Okay. But yes, in general, it's just yes.
Well, I mean, the one you just shown.
Exactly. Yes. Yeah. Okay. So now that the main problem, if you prefer automata, you can rephrase it as follows: given a finite automata A, just count the number of strings of length n accepted by this finite automata. Or similarly, given a finite automata A, sample uniformly from the set of strings of length n accepted by this automata. But if you don't like automata, that's completely okay. If you're not comfortable with them, we're not going to use this for the talk. We're just going to consider labeled digraphs. That's going to be the whole talk. Okay, so this sort of takes place in this broader setting of counting and sampling from formal languages. A formal language is just a way of defining some structured set in terms of some small machine, some small resource. And so regular languages are going to be the focus of this talk, these path labelings. But there's, of course, as you may know, there's a lot of generalization to this, and people have studied these for many years. One strong generalization is to consider trees instead of paths. And for some notion of what it means to be a tree, I won't define that here. So these are called the regular tree languages. And then even slightly more general than that are the class of context tree languages, which you also may know of. But if you don't, that's fine. We're not going to discuss them in this talk. But these become even more general in languages that are defined by restrictions of Turing machines. And so you can, the point is that you can ask this question, this simple question of any one of these formal languages. And it's the same question, and you can ask, how hard is it to answer this question? So this talk, like I mentioned, is going to be all about regular languages, these path labelings. But I'll just tease at a recent result that we've extended this result using some new techniques to this much more general class of regular tree languages. But I won't describe that in this talk. Okay, so why do people care about this? Well, there actually is quite a few applications in practice for why you would want to uniformly sample or count the number of strings. And actually, most of these applications seem to come from comp bio, where a lot of your biological sequences can be modeled by small formal languages like a finite state machine or a context-free grammar. And then there's some reasons why we might want to count or sample, such as providing random test data. And there's also a lot of other applications in knowledge compilation. Counting solutions to constraint satisfaction programs is a very constraint satisfaction problems is a very interesting application of this to me. And also other things in PL, basically. But I mean, the main point for me is that maybe they're not studied so much right now, but as far as I see it, finite automata are kind of this fundamental thing in computer science. And I think this is a really natural problem related to them. And I think just because it's so natural and simple, it's mathematically interesting on its own right. So I'm not so necessarily interested in the other reasons, but I think this is interesting enough on its own right. But there are some others. Okay. So now I'm going to fix the notation for the talk. Again, we only have two fixed vertices, u and v, and a graph G, and some integer n. And we care about path labelings between u and v. Okay, so now I'm going to define this notation of some natural notion of a subproblem. So Li of x is going to be the number, where x is a vertex in my graph. It's going to be the number of path labelings, it's going to be the set of path labelings of length I from the start vertex u to the vertex x. So this is just some natural notion of a subproblem. And in this context, what we care about is ln of v, which is the number of path labelings of length n from u to v. And I'm going to let the number m, the letter m, denote the size of the representation of the graph, like the number of vertices plus the number of edges. Now this might be a little bit frustrating to some people because I'm using n to denote the length of the path. And I'm using m to denote the size of the graph. I know sometimes n is the number of vertices, but for now n is always going to be the length of the path, and m is going to be the size of the graph. Let's just say the number of edges, plus the number of vertices. Okay, and our goal in this talk is polynomial time algorithms in both n, the size of the path, and the size of the graph. And I'll briefly note that if you want algorithms that are like 2 to the n time or 2 to the m time and polynomial the other parameter, you can get these, but we want fully polynomial. We want polynomial both parameters. And so if you want, you can just think of these both being polynomially interrelated, like one is not exponential in the other. Okay, and then finally one quick definition that we'll use a couple times in the talk. For a set S, I'm going to call an algorithm an epsilon approximate uniform sampler for that set if it samples an element from that set from a distribution which is within 1 plus or minus epsilon of the uniform distribution. So it's just going to return any element A from that set with probability between 1 plus or minus epsilon of 1 over the size of the set. So it's going to be nearly uniform. Okay, so now I'm going to talk about some special cases of this problem that might be of interest. So remember the problem is counting path labelings from u to v of size n. So suppose I gave you the following promise. I told you that for every vertex in your graph, every vertex x, and every possible edge label a, there's at most one outgoing edge from x with that edge label. So you look at all the outgoing edges from your vertex and you look at all the edge labels, none of them are repeated, they're all unique. So if I gave you this promise, does anyone see how we could potentially get a good algorithm for counting the number of path labelings in such a graph? Yep.
Well, those are just the edges, like you had with the same problem you already solved.
Sorry, what do you mean?
The same problem you already solved because each of those, every path's going to have a separate sequence of
Exactly. So if I gave you a labeling, if I gave you a path labeling, I look at the first label that tells me which edge to take. There's only one such edge, and I look at the second label that tells me the next such edge. So from the label, I can reconstruct the path. So there's a bijection between paths and path labelings. So we just count paths, and we already know that we can do that easily. Okay, good. So this problem, to answer your question, this is just what it means to be a deterministic finite automata. So in the case that your automata is a DFA, you only have one labeling. This is called an unambiguous grammar, and this is an easy problem to solve. Okay, good. So now I'm going to talk about some of the history of this problem and how it's been studied. So as I briefly mentioned, some generalizations of this and some other special cases can be solvable in polynomial time. But unfortunately, the problem is sharp P hard in general. And if you don't know what the class sharp P is, it's a pretty difficult complexity class, but essentially what this means is there's not going to be any exact polynomial time algorithm for the problem unless P equals NP. So we won't be able to solve this problem exactly. And I'm sort of going to briefly put this up here, but this is this class has actually been used to define a complexity class, this problem, which is this complexity class span L of counting the number of strings accepted by a finite automata. And this complexity class has a lot of interesting properties. It's a log space counting class, and it's almost as hard as sharp P. And it sort of generalizes the span P complexity class, which has been studied a bit. So there's also some interest in the complexity literature for this problem, but well, let me turn these back on. But we won't talk about this complexity literature here because it's not entirely important. Okay, good. All right. So what's been done so far? Well, you may know, and you may know from like other sharp P complete problems, that being sharp P complete doesn't rule out the fact that you can have an efficient approximation algorithm, like for instance counting solutions to DNF formulas. So this is actually exploited first by this work of Kannan, Weidek, and Mahaney in '95. They gave a quasi-polynomial time approximation algorithm for this problem of counting path labelings. And this was extended 2 years later by Gore and Jayaram, and then in a joint paper using similar techniques that I'll discuss a little bit, to give a quasi-polynomial time approximation algorithm on QPRAS for the set of all context-free languages, which is, let's say, a generalization of this problem we're looking at. And this also implies a QPRAS for these other regulatory languages that I mentioned. Yep?
QPRAS, quasi-polynomial, what's the R?
Randomized approximation scheme, yeah. So there's always going to be some failure probability. I'm not going to really talk, let's not worry about that. Okay, so, but sort of the thing is that it was open until very recently, since these two papers, whether there's any polynomial time algorithms at all for any of these counting problems for ambiguous machines. And so that's sort of the focus of this talk. And so our results, our first result, as we sort of hinted, is a FPRAS, so fully polynomial time randomized approximation scheme for this problem. So we have a polynomial time algorithm in n, the size of the graph, and 1 over epsilon that outputs an estimate within 1 plus or minus epsilon of the true number of labelings. Good. So this is a FPRAS for this problem. And similarly, the very related result is that we obtain a uniform sampler such that with exponentially high probability, let's not quite worry about that, and this algorithm outputs truly uniform samples, not even epsilon approximate, truly uniform samples from the set of all path labelings. So this is going to be strictly stronger than being an epsilon approximate sampler. And these two theorems, I wrote them as two different theorems, but really it's going to be the same algorithm, and they're going to build off of each other. So we'll see that. It's better to think of them being the same. Yep.
It's the same algorithm, but you have to do different things, or like by setting up parameters in the algorithm, you get the second theorem from the first one?
So you run them at the same time. So you can imagine doing this for every subproblem, and then you run one, and then you run the other, and then you build it up. We'll see. Yeah. But you can imagine that like the success of theorem 1, conditioned on having some value r that satisfies this, then you get a sampler that you can run it as many times as you want. Every time is polynomial time, and you always get a truly uniform sample. If your estimate is not good, I'm not going to give you any guarantee. Okay. So now I'm going to give an overview of the algorithm.
Could I ask one more question about the result? How does this contrast with the previous result?
So the previous
what was that?
So yeah. Oh, sorry. So I didn't define what so quasi-polynomial time means n to the log n. So like n times n.
Oh.
N. So it's like the input size to the log of the input size,
okay.
or like 2 to the log squared to the polylog. So this is polynomial as opposed to quasi-polynomial.
So Rajesh, one more question. So if this was an approximate sampler, then the equivalence between theorem 1 and 2 would be just like a general.
Yes, yeah. So I didn't mention that here, but there's sort of a general result by Valiant, Vrazirani, and Jayaram that says that actually if I replace this with a epsilon approximate sampler, then theorem 1 and theorem 2 are equivalent. One implies the other. But actually note that because this is stronger, theorem 2 actually implies theorem 1 just by this result, this classic result, but not vice versa. So this is stronger than approximate. Yeah. Okay. So I'm now going to talk about the algorithm, and to do this, I'm sort of just going to we're going to think about this in a dynamic programming fashion. We're going to look at these subproblems and look at writing them in terms of other subproblems. So remember, we defined this this set Li of S as the number of as a set of path labelings of length I from my beginning vertex U to any vertex S. And note that we can sort of write this in as a union of a bunch of non-disjoint sets. So how do we write it? Well, we look at every edge, Rs, coming into S, and we take the union over the set of path labelings of length I minus 1 going into that vertex R, appended to the label of that edge going from R to S. And then we just take the union over all the vertices, over all the edges coming into my set S. So this is similar than before. Remember that if all the edge labels are distinct and all the path labelings are distinct, this union is a disjoint union. So if I want to estimate the size of this, I just sum over the sizes of these. But in general, the issue is this is not going to be a disjoint union. So we sort of done this dynamic programming thing where we've written these sets LIR recursively as unions of other such sets with the smaller size, Li minus 1, the set of paths of length I minus 1, path labelings. So we're going to sort of do this inductive thing where we're going to compute estimates to the size of each of the sets, path labelings of length I going into S. And we're going to first estimate the path labelings of length I minus 1 and then use these to estimate the path labelings of length I. This is a standard dynamic programming approach. And again, the issue is that this union is not disjoint. But if it was disjoint, having estimates of the prior layer would be sufficient. But because it isn't disjoint, we're going to need to do something more than just have estimates. We're going to need to be able to sample from these sets uniformly the number of path labelings of length I minus 1 going into our vertices R. So now we'll see why that's going to be sufficient. And we're sort of going to say this in a general framework. So this sort of slide shows you that if you can sample, you can count. So let's suppose I give you some arbitrary set S that's a union of k other sets. S is a union of Si from I equals 1 to k. I'm going to give you the promise that you have, let's say, approximation to the size of each set Si. You have an approximation to the size of these guys. And I'm also going to give you the promise that you can sample epsilon approximately from each of these sets Si. And what you want to do is get an estimate of the size of the overall set S. So how can you do this? Well, there's kind of a straightforward way to do this. Well, what I'm going to do is I'm first going to sample one of my underlying sets, Si, with probability approximately proportional to its size. I don't know its size exactly, but I have an approximation, so I can sample it with close to the right probability. Now let's say I sample this set 2. What I'm going to do now that I have S2 is I'm going to sample an element uniformly from the set, or epsilon approximately from the set.
Now you sample a number of things You say the size of your sample is proportional to the size of the set?
So I'm going to just choose one of these k sets. So I have the sets S1, S2 up to Sk,
Okay.
and I'm just going to choose one of them,
Okay.
and the probability that I decide to choose it is proportional to my estimate of how large it is. So now I've chosen it, and now I'm just going to sample an element almost uniformly from it. And so let's say I get this element A, and then I'm just going to look back and I'm going to see how many other sets contain my element A. And I'm going to call that value C of A. So note this, the C of A is going to show up a couple times. C of A is just the number of times I overcounted this element A in the union. So if the union was disjoint, C of A would always be 1, and I just output the sum of all the elements. But instead I need to compensate for this overcounting. So what's my output? It's just the sum of all the sizes, my approximations of the sizes, multiplied by 1 over CA, which is like sort of giving me an estimate of how much I'm overcounting. So sort of because this C of A value is always at most the number of sets, it's always at least 1 over k, and so I can just sort of apply standard Hofstadter bounds, and if I do this enough times, polynomially many times, take the average, I'll get a good estimate. Yep?
So the point is that checking for C of A, or checking whether A belongs to one of those guys, is doable.
Yeah, so I wasn't going to mention this, but for whenever I ask, is the element in the set, for all the things we care about here, well, there's an efficient way to test membership. Like for instance, if this is a path labeling and I want to know if you can get from one U to some vertex without labeling, I can sort of just do a breadth first search at every step. I only take edges that have the right label, and if it's reachable with those labels, I say yes. And so there's like a linear time algorithm for this membership test. Okay, good. All right. So this fact that what I just said is that counting and sampling of the smaller sets implies counting of a union is going to suggest this high-level approach. Well, like I said, we're going to inductively compute estimates of these set of path labelings. So I'm going to let my estimate of the size of the number of path labelings of length j going into vertex r, I'm just going to call that njr. So that's my estimate. And I'm going to compute these estimates inductively. And I'm just going to have this first induction hypothesis, which is what you would expect. I'm just going to say that this induction hypothesis says that these estimates are good estimates. They're close to the true value. And the last slide just said that if we have these approximations, these good approximations of the true set sizes for some size I, and if we can also sample from the set of path labelings of size I, then we can bootstrap that to get an approximation for the set of path labelings of length I plus 1 for any vertex. So what this suggests is there's only one thing we really need to do, and this is going to be the hard part of the problem. We just need to sample from these sets, LIS. Now we've seen that basically the main problem was theorem 2, the sampling problem. So for the rest of the talk, we're going to look at the sampling algorithm, which just says, I just want to sample from the set LIS, given that I already have approximations of the smaller sets. Good so far? So this is just the last thing we need to do. So now we're going to talk about the sampling algorithm. Okay. So the first thing I'm going to describe is sort of a general sampling algorithm for unions of sets that was used in the prior work with some nice results and has been actually shown up a lot in history. So this is called Karp-Luby sampling, and this was originally used to get an FPRAS for counting the number of solutions to DNF formulas. This is sort of a classic result, and it's in sort of the same setting as earlier. Suppose I give you some set S, some arbitrary set S, that's a union of m other sets Si. And let's suppose for now I told you exactly the value of the sizes of the sets Si. And I also told you how to uniformly sample. I gave you an algorithm to uniformly sample from each of the sets Si. And I asked you to sample from the set S. Well, so how could you do this? Well, you can sort of do something similar to the same thing we did before. Well, I'm just going to sample a set, one of the SIs, with probability roughly proportional to its size, or exactly proportional to its size in this case. I just sample an element uniformly from that set. Now I step back and I compute the same value before. How many times was that overcounted? So here I got this element A, and I see that it was in 3 other sets, S1, S2, and S4. But I want a uniform sample, so some other elements may have only been in one set, and those elements would have only gotten 1 chance to be sampled. Here, A had 3 chances to be sampled. So I need to reject it so that it's not being oversampled with too high probability. So what do? Well, I just choose to accept it with probability 1 over the number of times it's overcounted. Otherwise, I reject it and do this again. And so in this case, A was overcounted 3 times. I'm just going to keep it with probability 1/3. Otherwise, I throw it away and I repeat it again. This will give me a truly uniform sample from this set. Good. So I sort of described this here in a general set, but how does this relate to our algorithm? Well, you can actually apply this in a fairly straightforward way to the problem. Well, remember we have this union here of non-disjoint sets. So what can I do? If I want to sample an element uniformly from Li plus 1 of S, path labelings of length I plus 1 going into S, well, I already have estimates of the size of the path labelings of length I, and appending an element doesn't change the number of path labelings going into each one of these sets. So what I can really just do is sample one of the edges coming to my vertex S with probability proportional to the size of that edge. And what do I mean by the size of that edge? I mean proportional to the number of path labelings that go through that edge. I already have approximation of that. So good, I've sampled an edge, E equals RS, so probably approximately proportional to its size. Now I'm just going to recursively, using the same procedure, ask for a sample of one of the path labelings going into that vertex R, where R is the vertex that I just sampled the edge from. And then at the end, once this recursive procedure returns, I'm going to accept that element A with probability 1 over the number of other edges, which could have also produced that sample. And this is going to give an approximately uniform sample, and then I'm going to return that label that I got appended with the label of the edge that I sampled. Okay, so what's the issue with this? Well, sort of the analysis is that I'm recursively calling this on itself, and each time I call it, I have some rejection probability. And in the worst case, this rejection probability is like 1 over the number of edges coming into the thing, and this can happen roughly every time. So the acceptance probability is becoming exponentially small in the depth of the recursion. So it's like going to be like 1 over the size of the graph to the depth of the recursion, which in this case, as I've described it in this naive way, it's going to be n. And so the reason I brought this up is because using some very nice, clever depth reduction techniques, Gore and Jayaram, this was actually what the sampling algorithm they used was along with one step of depth reduction to get a quasi-polynomial time algorithm. So all they did is Karp-Lewis sampling, but they did something clever to reduce the depth to log n, and then now you get a quasi-polynomial time algorithm. And I won't say anything more about that, but the quick teaser is the main technique they used was this classic depth reduction result for arithmetic circuits. They sort of translated the problem into a problem of polynomials, but I won't say any more about that.
Did that use the same framework you just showed?
It uses exactly the same algorithm, but they first reduced the depth a little bit. So they did Karp-Lewis sampling, this recursive thing, but then they showed that you can reduce the depth in a way that you don't recurse n times, you only recurse log n times. But the reduction probability each step is like 1 over m times n, so it's quasi-polynomial and not polynomial. Okay. So sort of the issue with this Karp-Lewis sampling paradigm is that the way it deals with this problem of sampling from non-disjoint sets is it has a rejection probability to normalize the fact that some things are going to be overcounted. But the issue is like our problem is naturally the issue, like things are going to get overcounted a lot. And this is always going to have some exponential dependency on the depth of the recursion, because I'm rejecting something that was like even probably 1/2 every time in the best case. Well, not in the best case, but like in general, I'm going to have exponential dependency on the recursion depth. So we sort of need a new method to sample uniformly, which doesn't involve the sum rejection step. And that's going to be the point, the sampler we introduced now. And what I'm going to do is describe this general framework. I'm going to call it partition to sample, but this is not really anything new. This is probably done a billion times before. But I'm just going to describe it in sort of this general way so we can see how we're going to implement it. So we know that what we're doing when we describe it. So suppose I give you some arbitrary set S. And for now, suspend disbelief on other things I'm going to do. I'll tell you how we're actually going to implement them in a second. But let's suppose that I told you, I gave to you a cut. I gave you a partition of my set, S into S1 and S2. And suppose you also knew the sizes of these parts, S1 and S2. Well, I can just choose one of the pieces with probability proportional to its size. So in this case, I flip a biased coin, and I choose S1. And then I just throw out S2. I don't look at it anymore. And then I just recursively apply the procedure to the set I chose until it just has only one element. And at that point, it's going to be a uniform sample for me just to return that. So what am I doing here? Now I have S1. I'm going to cut it up again into some partition, into S3 and S4. I'm going to flip a biased coin. Let's say it chooses S4. I was more likely to choose S4 because it's slightly larger. And I'm just going to repeat this process. Cut it up again, flip a coin, and choose one side. And I keep doing this until there's just one element. This is just sort of a high-level simple thing that is a way to get a uniform sample. And what we're going to do is we're just going to approximate this second step. In some way, we're going to figure out how to partition our set. And at each point, we're going to figure out, importantly, how to estimate the sizes of each of the pieces in the partition. And if we can do that, note that like we saw, essentially, what is this doing? It's creating a nested sequence of sets, SI1, SI2, SI3, up until there's only one element. And so if at each step, I got a relative error approximation of the right probability with which I should be flipping my coin and recursing into the right set, then I would get a relative error approximation of the actual value 1 over the size of the set. So for now, that's going to be my goal. I'm just going to try to get a relative error approximation of each of these partition probabilities. And I also, of course, I need to tell you how to partition this set. So now that we have sort of this general high-level approach, let's get back to our actual problem. So remember, we have this vertex S, and we want to sample from the set of path labelings of length I+1 going into S. So let's just look at this specific example here. Let's suppose S has exactly 4 edges coming into it from these vertices R1 to R4. And let's say the edges are labeled 0, 0, 1, 1. So can anyone think of sort of a natural way to partition this set of all labelings going into S? Sorry, what?
Based on the label?
Which label? Yeah, exactly. So all the path labelings coming into S, they have some last bit. It's either 0 or 1. If it's 0, it better go through one of these edges. If it's 1, it better go through one of these edges. So remember that this thing is a union over edges coming into S. So I'm just going to partition it based off the edges. The edges with this label 0 and the edges with label 1. So I'm going to let S0 be all the edge labels, the end of the label 0. Well, that's just the set of all labelings going into either R1 or R2. And then I append a 0. And then similarly, the set of edge labelings with a label 1 at the end must either go through R3 or R4. And then it has a 1, and then I append a 1 at the end. And of course, these sets are obviously disjoint because I can't have both a 0 and a 1 at the end. Okay, so what do? Well, I just need to estimate the size of each of these pieces of the partition, the ones with label 0 and ones with label 1. And so that size is the number of labelings of length I going into R1 and the number of labelings of length I going into R2. And remember, I already have estimates of both of those sizes. But this union is not disjoint, so I don't actually have any way so far to estimate the size of this union. So let's get back to that, and let's just assume for now that I was able to estimate the sizes of these pieces, that I had some algorithm that told me how to estimate the size of this union, even though it's not going to necessarily be a disjoint union. So let's just assume for now we have that, and we'll get back to that. So let's suppose I have an estimate of the size of each partition, n0 and n1. Well, what can I do? I just do what the approach said. I just flip a coin where the bias of the coin is proportional to my estimate n1 and n0, and I sample a bit, either 0 or 1, with probability proportional to my coin flip. And so let's say in this case, I sample the bit 0. Well, now what I want to do that I've sampled that bit is I want to condition on that bit. I want to sort of now sample the rest of the prefix, condition on the fact that this last bit is 0. So how can I do that? Well, I'm going to look at the set Q0, which is the set of all vertices that had an edge into my original vertex with the label 0. Because conditioning on the label 0 is the same as saying I better be at a vertex from which, taking the label 0, I can get to my final vertex S. So the set Q0 is just going to be the set R1, R2 in this case, because these are the only vertices that had a label with the edge 0 into it. And so now what do? Now I'm going to forget about S, and I'm only going to look at the set Q0. And so I'm going to look one step further, and I'm going to look at all the edges coming into my set Q0 with any label. Okay, and I'm just going to do the same thing over again. I'm going to partition the edges between 0 and 1. I have this S00, which is all the ones with 0 into it, S01 with all the edges with the 1 into it. And just note, like a quick thing here for sanity, this vertex Q1 is included on both sides because it has the edge with the label 1 going into one of these vertices. It also has the edge with the label 0 going into one of these vertices in my target set. But it's not an issue for disjointness because in one case it's getting counted here, but it'll be counted with a 0 at the end. And in one case it's getting counted here, it'll be counted with a 1 at the end. So this set S0, S1 is still going to be a partition when I append a 0 to one case and a 1 to the other. So again, what do I need to do? I just need to estimate the sizes of these sets. So again, let's just assume that I can do that. Let's assume somebody gave me good estimates of the sizes of these sets. I just flip another bias coin again, and I choose the bit. I condition on a bit. Let's say I choose I2, so I condition on a bit I2 between 0 and 1 with the right probability based on my estimates. So let's suppose that I chose the bit 1. So let's suppose that I flipped a coin, it landed heads, this bias coin. And now I'm going to condition on this suffix that I'm now growing. So now I condition on the suffix 10. And again, I look at all the vertices, Q10, which had the edge with the label 1 into my prior set Q0. And now I'm just going to repeat this process with this new set of subset of vertices, Q10. So at each step, I have a subset of vertices. I'm looking at all the edges into it. I'm picking one of the edge labels, and then I'm just moving to the set of vertices that had that edge label into my prior set. And this is sort of representing what it means to condition on this prefix. So continue with this set, right? So what are we doing? In summary, this sampling algorithm, the approach is to sample a prefix by, a suffix by growing the suffix of the label. We're not sampling a path, we're sampling a suffix of the labeling. So at each step, I have some suffix W that I've conditioned on. And now I want to sample the next bit, condition on this suffix so far. So the way to do that, and sort of the punchline for why this algorithm works, is because there's sort of an easy way to represent what it means to condition on this suffix W. And all that means is that if I want to condition on the suffix W, I just have to get to one of the vertices from which, taking W, I can get to my final vertex S. And it doesn't matter which one I get to, so I only need to look at the path labelings going from U to one of these vertices QW, which is the set of vertices that have this label, that has from this label W, you can get to the vertex S. Is that good? Okay. So this is what we're going to try to do. we need to sample a prefix from this thing, and we can always partition this set, the union of all the labelings into Q0, by appending a 0 in one case and appending a 1 in the other case. And this is always going to be disjoint, and we just need to estimate the size. Right, so what's the only thing we have left to do that we skipped over? Well, we have to estimate these pieces, because we need to figure out what the bias of our coin should be that we flip at every step. As we're flipping this n times, and each step we're using this bias. So how do we estimate these? So we've now reduced to the following sort of general problem. Suppose I gave you any subset of your vertices. Just estimate in some size, let's say j, which is less than our current size I. Estimate the union of all the path labelings going into one of these vertices. This is the exact same problem here. I just have some subset of vertices. I want to estimate the union of their path labelings. So I'm just writing it in a general setting. So my goal, if I could do this, I claim that basically everything else is done. I mean, the algorithm I described to you only needed to be able to do this. So the first thing you might say is, actually, hey, we already have approximations of each of these inner sets, LJR, because we've computed those approximately. And you just told me that if we can sample as well, then we can get approximation of the union. So why don't you just sample from these sets? But of course, remember that what I'm explaining to you right now is the sampling procedure. So I can't go recursively sampling from these sets because it'll cause an exponential recursion. So I need some other way of doing this. Your second sort of maybe guess would be, well, you have estimates of the sizes of each sets, but the issue with the union is it might have some intersections. So why don't you store all possible pairwise intersections between these sets and keep an estimate of that? Or more generally, store k-wise intersections. But of course, as you might know, you can't really truncate this inclusion-exclusion formula. You need to keep all the intersections if you want a general approximation. So that's way too many approximations to store, so we can't do that. So instead, I'm just going to rewrite this equation in the following way to sort of motivate what I'm going to do. So I have this union of path labelings of length j going into some subset of vertices. And I'm just going to rewrite it in sort of the following natural way. I'm going to order them, and I'm just going to subtract off the prior ones at each step. So this is just something straightforward here. What am I doing? Well, if I have three sets A, B, and C, well, the size of the union of A, B, and C is just the size of A plus the size of B with A removed, and plus the size of C with A and B and A and B removed. That's all I've done. And now I'm just going to multiply and divide by the same value, which is the size of this set, LJRP. So this is just saying the sum of the size of the union is the sum of the sizes of the sets, where at each point I multiply by the fraction of the set which was contained in prior sets. And so now you might note I already have an estimate of the first term, so all I need to do is estimate the second term. So I've reduced the problem even further. I just need to estimate terms of this form, which is the ratio of one of my set of labels, which is contained in some other subset of labels. So I'll formalize that again in a general way. This is, again, an even more cleaner version of the problem and a more reduced version of the problem. All we need to do, given any subset of your vertices, and given any distinguished vertex R, estimate the fraction of the path labelings into R which are not contained in one of the path labelings into one of these vertices in my set S. And if I can do this with relative error, if I can estimate this, then I'm good. Then I can solve the problem. So sort of the key and the key step, which is not terribly complicated once you see it, but sort of crucial to the algorithm, is instead of trying to store approximations or some deterministic quantity, we're just going to store sketches of each of these sets. So what's a sketch? Well, I'm just going to, for each of these set of path labelings of length j into R, I'm just going to store a polynomial-sized subset of uniform samples of those labelings. So I'm going to call this set UJR. And I'm calling it a sketch because basically, whenever I want to estimate some quantity of my set LJR, I'm just going to pretend that UJR is that set and see what fraction of elements is contained in that set. So I just have the set UJR, which is a subset of LJR. And note that this j is less than the current I that I'm thinking about, so I can sort of inductively compute these. And if I have these, and if they give me good estimates, then I can sample on the next step and build these sketches again. And so I'm going to build these sketches for each level inductively. So let's just see briefly how a sketch can help us solve this problem. Well, what am I trying to do? I'm just trying to estimate the fraction of a set which is contained in some other subset of it. Well, I can just look at my sketch U instead and see what fraction of my sketch U is contained in this other set. So what's the simple picture? If I have just some arbitrary set L, it's too big to store. Instead, I keep a random subset U of the elements in this set L. And let's suppose I had some cut through my set, L1 and L2. And I wanted to estimate, say, the fraction of the cut that lies on one side. Like what fraction of the set L is consistent of elements in L1. So I want to estimate like the ratio of L1 to L2. But because I don't have L, what I can use instead is just use my sketch. So I can look at my sketch U and say what fraction of the points U are on the L1 side of the cut. In this case, it's exactly half of my points. And so I use the estimate, the number of points in U that are in L1 over the total number of points in U as just an estimate of, the actual thing that I'm trying to estimate. So this is sort of a rough idea of how we're going to do this. And I'm not going to state formally what we condition on because there's some minor technical details, but we're just going to add one more induction hypothesis, which is that these sketches that I have satisfy some deterministic criteria that allow all possible estimates of the form you just saw on the last slide to give you a good estimate of the right fraction. Now there's exponentially possibly many queries you can make. You're only going to make polynomially many. But we can basically condition on the fact that all of them would be true regardless of which ones you queried for. And if we just add this induction hypothesis, we were able to show that if you can, this will allow you to get samples in the next step. And then you use these uniform samples to build your sketch for the next level. And then you keep doing these conditioning on this high probability event. And then at the end, you get your estimates. So just a quick wrap up. All we did was we had these two induction hypotheses. One was the pretty standard one. We just kept estimates at each step and used them to build estimates in the next step. So the first hypothesis was that my estimates of the sizes were good. And then my second hypothesis was that the sketches of my sets were good for some definition of that, which just means that it gave me good estimates for anything I could possibly query to it.
So Rajesh, can I slow you down for a bit? So what's the claim on the sketch you're making? Can you go back one more slide?
Yeah.
So are you claiming that you're going to have these, the notion of equality is relative closeness?
I
don't think it's possible under what you're doing.
No. So you get additive error, right?
Okay. Yes.
If this set is big, so we're trying to estimate a union.
Yes.
So let me go back to the sum. So we're trying to estimate the sum. So note that the first set, this fraction is always like there's no fraction in the first set. I'm not cutting anything out. So if I go on and suddenly this fraction becomes too small, I'm cutting way too much out. So this becomes, say, this is exponentially small. Well, then I'm cutting so much out that I actually don't care. It's not going to affect I'm just trying to estimate the sum. That's all I'm trying to do. So if I'm not getting relative error, it's so small that it doesn't matter. But yes, but like in general, I'm only going to get Hofting additive error. Yeah, so
the algorithm is going to keep track of these, it's going to build these sketches.
Yeah.
At any time,
it stores them. It doesn't. You don't adaptively build them. You compute them once and then you keep them, and you condition on them having some deterministic property that lets them be good for any possible estimate.
So it's a pre-processing step to compute all these sketches. It happens as you go, as you're generating it.
Well, because to sample uniformly for the paths of length I plus 1, I have to have sketches of the paths of length I, and the sketches of the path of length I minus 1, and all the way down to 1. But once I have those sketches and those estimates, if they're good, then I can sample uniformly from the paths of length I plus 1, and then I can build my sketches for this, and then go on like this. So I'm doing them back and forth, estimate sketches, estimate sketches. And so I condition on these two hypotheses, like for a given value I condition on both of these things being good for that, and then condition on both of these induction hypotheses being good. I get them to hold for the next step with high probability. Okay, so is the high level of the algorithm clear? Any questions? Okay, so a couple things that I didn't mention in this talk. So the first thing you might complain about immediately is that everything I just described to you was an approximate sampler. Each step I'm approximating the probability which I flip a coin. And at the end, I'm only going to get approximately uniform sample. And you may say, well, maybe this is okay. We only usually want approximate samplers in FPRASs. But actually, this is not going to be okay. And the reason is that if I settled for an epsilon approximate sampler, note that the error of the sampler depends on the sketches from the prior steps and the errors of the estimates. So this error is going to feed back into the error of the sampler in the next step, and the error of the approximations in the next step, which are going to feed back into the error of the sampler. And I'm going to get a geometric blow-up and the error at every step that I do this. So actually, it's not going to be okay just to have an epsilon approximate sampler, because I'm doing this recursively at n times, this iterative step process. So I need some way to remove the error of the sampler completely. I won't formally say what it is, but I'll just say that there's a straightforward rejection, relatively straightforward rejection step that you can apply. And I won't say formally what it is, but the punchline is, so I sampled some element A for my set. And I didn't sample it with truly uniform probability. I didn't sample with the right probability. And I don't know exactly the size of the set. But what I do know exactly is I know exactly the probability with which I did choose to sample that element A. Because all my algorithm is doing is at each step I flip a biased coin, and I know exactly what the bias of the coin that I'm flipping. And I flip a bunch of coins, and so at the end when I have my element A, I can compute exactly the right probability with the probability with which I did choose to sample A. And I have sort of an estimate of the size of the set already, and I know like roughly what it should be, and I know what it was. And so I can compute a rejection step that normalizes the distribution. And the rejection step will only have, like, say, probably 1/2 of being a rejection. So it's not gonna, there's not going to be any small issue with acceptance probability. So that's all you need to know about that, and that makes it a uniform sampler. And once we do that, then this sort of breaks the feedback loop of error flowing in and out of the samplers. And there's also some slight conditional dependencies of the sketches that I won't mention that they're really not important. But the summary is basically everything.
It's kind of like the problem of if you wanted to pick a uniform point in a circle, you pick a uniform point in a square, and then throw it out if it's not inside the circle.
Yeah.
Is that what you mean by that?
Well, roughly. So suppose that I have an element, a set of a size 100. I have 100 elements, and I sample approximately uniformly from it, and I get an element A. But suppose I look and I could see what probability I chose A, and let's say that I chose A with probability. Like 1/200. Let's say 1/50th. So I oversampled it. It should have been sampled with probably 1/100th, but I sampled it with 1/50th. I don't know what the value 100. I don't know what the true size is, but I have an approximation. Say I have an approximation 150. I know that it's between 50 and 150. So what I can do is I can sort of reject it with a probability, the actual probability that 1 over the probability that I sampled it, times like 2 times my approximation. So I might write this down, but basically, if I sampled it with higher probability, then by rejecting probability proportional to 1 over the probability, I cancel that out. So actually, this is actually just really straightforward. So if I sample something with probability p, and I know exactly the probability p that I sample it, so I sample something with probability p, well at the end, I know p exactly. I just reject with probability 1 over p times some value 1 over n, so that this is bigger than the actual size of the set. So these cancel, and now the probability that I sample an item is independent of what the item was. It's just some fixed value 1 over n, and as long as n is larger than the size of the set, this will be a uniform sampler. So because in particular, this has to be a probability, so this just needs to be bigger than whatever this could be. But there's nothing too tricky going on there. It's just we can do this because we know exactly the probability which we did sample the element. Okay, I want to get to some conclusion statements. So that's all I wanted to say about this algorithm. I think it's a really interesting result. Nothing too complicated going on, but it was kind of an open problem for a while. So it was interesting that some of these problems that they are, and I'll mention that in a second. So just a short summary and conclusion of what we did. So we gave the first polynomial time randomized approximation scheme for this problem of counting strings accepted by a finite automata. And this is also the same as this problem of counting path labelings. And as I mentioned, there's this new result that we have that is extending this quite a bit using some new techniques to this much more general class of trees, where now instead of going from one vertex to one other vertex, you sort of jump to multiple other vertices, which themselves can move to other vertices and so on. And this is called the regular tree languages. And the main sort of high-level takeaway from the algorithm is instead of having this recursive rejection step, we just sort of have this approach based on recursively partitioning the set we're trying to sample from, roughly approximating the size, and flipping a bias coin. Right. And the tree sampler needs some new techniques, but that's probably a different talk, subject of a different talk. Okay. And so there's actually a lot of open problems in this area that I wasn't aware of, and that I'm actually pretty interested in. So one of the biggest ones is that, as you may know, people that have worked in FPRASs, if you've done some of this, Markov chains, MCMC, this is kind of like one of the most prolific techniques for designing polynomial time approximation schemes. And it was sort of left as an open question in this Gore and Jayaram paper, and these guys know Markov chains pretty well, whether it was possible to design a rapidly mixing Markov chain to sample from these formal languages, any of them. And they sort of said that they tried this and they weren't really able to. And I also spent like a while trying to come up with a rapidly mixing Markov chain, and it sort of doesn't, it doesn't seem to be any natural ones that do. And I think this is actually would be a really interesting open problem, because if you could design such a Markov chain, I think you would get a lot of insight into the overall problem and actually be able to potentially use this to design FPRASs for a lot of other open problems which don't have polynomial time algorithms yet. Like for instance, CFLs are still an open problem, and generalizations of context-free languages are also still an open problem. And these things have a lot of applications that people in database theory really care about. So yeah, I'm actually, I think this is really cool, and I think it's pretty accessible too. So if anyone is interested, like I'm happy to talk about these problems. There's a lot of open ones here. And I wanted to end on one final, I don't know, some brief takeaway, which is that I would have never really known about this problem at all, or known about its like relation to other problems in the work if it wasn't for my co-authors who are experts in database theory. So like I consider myself, along with probably some of you here, to be more like, I guess track A in computer science is usually considered to be like algorithms and complexity, and track B is usually like more automata and logic and these sort of things. And I think maybe someone mentioned this is kind of like a good example of a work which comes out of sort of meshing ideas between the two tracks. Like my co-authors are experts in database theory, but I knew a bit about algorithms, and so we came together and studied this open problem that I would have never known anything about. So I think it's kind of like, there's a lot of things that I learned from these guys about database theory. I think there's a lot of tools that they have that are useful for algorithmic problems, and vice versa. So I think maybe if anyone, I think this is sort of like there's lots of open problem here, and I think that a lot of you would be perfectly suited to solve them. So if you want to talk about them, I'm happy to chat about them. Anyway, that's all I wanted to say. Thank you.
Would it change anything if you allowed edges with no labels? Like the empty strings?
Oh, you mean edges with no labels? You can always remove those. You can always convert this in, like if you know from Automata, you can always remove epsilon transitions. So if I add, I can always take my graph and convert it to a new graph that doesn't have any of these unlabeled edges, and has the same two vertices and the same set of path labelings between them.
The number of states doesn't blow up?
Just by a constant. Like you imagine, just. Any other questions?
Right. If there are no other questions, let's thank Rajesh.